as you have studied for the chapter 13 of the mechanics of material. We have studied about the column, and then we separate the column into the one of the short column and another one for the what's so called for the long column. And then for the short column from the mechanics of material, this short column will fail by the yielding of the steel. But for the long column, the failure will belong to the buckling. The buckling is a kind of stability failure. But for the short column over here, the failure is a kind of material failure. So they are totally different kind of failure. Okay. In this lab 12, we will study about the behavior and the modes of failure of the rectangular steel column with various stress ratio. That means we are going to study the steel plate with a given cross section, but we will vary the length of the steel plate. Some will be short, the other will be get longer. So the stress ratio of the column will different. Okay, and then we will put this specimen into the testing machine to determine the critical load. Critical load is P critical, and we can determine the critical stress by the critical load. And then we will plot the graph. That's going to be the graph of the critical stress, okay, with respect to the stress ratio. And then we will compare the graph from the theory with the experimental result that we have, and then compare it with the design equation. So this one will be the graph from the design equation, and this is going to be the test result from this lab. Okay, and the last one gonna form the theory. We will see the difference between them, and I should say that most of the time the curve from the design equation must be the lowest one for the safety of the structure, because most of the time the design code come from the testing result and then divided by the factor of safety. Okay, that is what we have. The bucking of the long column. Okay, there is two types of them. This is the picture from the lab that I used to be the research assistant to my professor. There is two different kind of buckling. One called local buckling. The local buckling occur in the thin wall structural member. Okay, and there is another one called the global buckling. Now we are going to involve with the global buckling, because the problem of thin wall structural member buckling is very complicated. You can have this one in the master degree. I teach this local buckling in the chapter 10 of the advanced mechanics of material. So now we focus our lab to the global buckling. Okay, in the global buckling, during the buckling, the stress occur in this column is less than the yielding stress. So the behavior of this one is a kind of the buckling of this plastic ruler. You push it, it's have the buckling. You release it, it's come back to its original range. So the behavior of this kind of column is linear elastic. Okay, and then I separate the column into the long column and short column. For the short column, under the axially compressive loading, the failure of this column is due to the yielding, if it is the concrete, or is cracking, if it is the concrete. Okay, it depends on the material. And anyway, if you consider the hot low steel, you can see the failure is a kind of yielding. However, when we talking about the brittle material, such as the concrete, such as the cast iron, we have the crack occur. Okay, crack occur in this kind of material. Anyway, we come to the ideal column. For the ideal column, the column will support one by the pin, another one by the roller, and it's going to be made up by isotopic homogeneous material such as the steel. During the buckling, the behavior is linear elastic. Okay, and the column is supposed to be very long and straight. Okay, and again, it's subjected by frictionless pin and the roller, and it has the force that's applied to the centroid of the section, and the buckling will occur only in one plane. Okay, Euler derived the equation. Euler said the buckling load that produces the buckling of the column can compute by using this equation, in which this is the number of the curve is occur if the column has just two support. It's going to have this one. This has n equal to 1. But if you put this one into at the middle and you put this one, you can see the buckling, the deformed shape of the column will have 2n. Okay, and then this is going to be the number of the curve that's occur in the column. And then the E is going to be the modulus of elasticity as we talking about it before. And the I is going to be the moment of inertia of the section. For example, if this one has the rectangular, it's jump a lot, has a rectangular. If it has a rectangular, something wrong with my this one. If this one has the rectangular, rectangular is going to have this kind of section. Okay, and the I in the section can be separated into two I. One is the I about this x-axis, and another one is the I about the y-axis. Okay, if this is going to be 10 millimeter, and this is going to be just 1 millimeter, you can see the I sub x is going to be 1 times 10 cube divided by 2. And our I sub y is going to be 10. It's going to be this one 10 times 1 cube divided by 2. You can see the I sub x is larger than I sub y. So the P critical also occur controlled by the I. And you can see the buckling of the column is like this. bacterial column is occur along the y-axis. So most of the time, this I in this equation must be the I minimum. Okay, and then L is the length of the column. Now, if n is equal to 1, this equation will provide the minimum critical load. This P critical for this kind of column shape is going to be the minimum critical load. Okay, if you put the n square, like I said, if the force here is 10 Newton, if you put this one at the middle, this is going to be 40 Newton. Okay, and more explanation about the I is showing here. There is two value of the critical stress. One compute basis on the I sub A. That is going to be I in this direction. And another one is compute by based on this. It's going to be this one. Since I sub BB is large, so the P critical will compute it basis on the I min. So I sub AA is used to compute the moment of inertia of this rectangular column. Okay, again, I show you like this. You can see the I sub X is here. Computed by this, the I sub X is larger than what we have for the I sub Y. So the buckling will occur basis on the I sub Y because the I sub Y will produce less P critical when the load increase from 0, 10, 20, 30, when it reaches 32.9, this column will buckle. It won't go to this 131.6. Okay, and based on this discussion, there is the critical stress. The critical stress is going to be the P critical divided by the A. And basis on this, we have what? Pi square E I over L square and A. Why Ajahn putting things like this? Because the I is the property of the section. I equal to B H cubed over 12. And the A also the property of the section. A equal to BH. Okay, and we define this one as the radius of gyration R square equal to I over A, and R equal to square root I over A. Okay, based on this equation will be pi square E divided by L square and half R square. And come to this point, somebody will say, this is the length of the column. This is the property of the section. So we define the stress ratio as the length divided by the radius of gyration R equal to square root I over A. And then this equation, just put the I down, we get the sigma critical in the form as this equation. Okay? And then this ratio somehow can be used to classify the column into the short and into the long column based on the stress, critical stress, and slenderness ratio here. And based on this equation, if the slenderness ratio is very small, the value in this small, the value of critical state can be get very, very large. Is that possible? No, it's not possible. The stress can be limited to the strength of the steel or the steel. That means we limit it to the yielding stress. Okay, so this portion is going to be the short column, and then this portion is going to be the long column, and there is a point that separate the short column from the long column, and at this point sigma sub y equal to sigma critical, and that means it's going to be equal to pi square e divided by L over R square. And can we determine the stress ratio at this critical point? Yes, it's going to be L over R as critical. It's going to be pi square E and divided by sigma sub y. By putting into this is going to be square. And then if you put the square out, it's going to be the critical stress ratio separate the short and the long column can be computed by this. For the steel, we just put the E and unit into this. We get this one for 88.86. That is about 89 here. Okay, and by doing this, we have the theoretical curve. Let me call this is going to be theoretical curve for steel column. Okay, and there is the design curve. Since the column are not the ideal column, the columns maybe have some error, such as in the construction process, the column is not very straight. It may have some eccentricity. Okay, and the material of the steel column maybe have some residual stress due to the manufacturing process, and the column support may not be the pin and the roller as we discussed based on the Euler bucking loading, and also the axial loading that apply to the column may change in the magnitude and the direction change with time. Okay, and by doing that, most of the column design equation come from the empirical equation. That means most of the column equation basis on tests of column. Okay, so by doing this, we have this kind of Euler theoretical curve. Okay, and this theoretical curve also limited by the sigma sub y of the material. And if this is the steel, you may recall from the previous lecture, this is going to be L over R critical or critical stress ratio. But when we test it, we will get another curve. Okay, this is going to be the curve that we fit for the testing data. There is a lot of point here for the curve, and since the design equation bases on the test, we will have another curve that's for the design by putting the factor of safety, okay, to the test result and to the theoretical result. By doing this, we have the steel column design curve basis on the AISC, okay, which is the American Institute of Steel Construction. Basis on this, again, there is the critical stress ratio that separate the column into the short column and the long column. For the long column, you can see this is going to be the equation for the Euler equation. If you set for the column with the pin roller this K gonna be 1. And you can see this sigma allowed is going to be sigma critical divided by what? Divided by the factor of 23 divided by 12. That is close to 2. Okay. The complication occur for the short column. They let the highest point of this one to be 0.6. So that means sigma allowed is only 0.6 of sigma sub y here. Okay, and then the graph here will follow the equation over here in which the factor of safety change. You can compute the factor of safety by this equation in which the critical, if this is 1, criticalness ratio can be computed based on this. And as you see, this is about 89 from the previous slides. So you can compute the factor of safety. If this one is about 89, so the factor of safety just check with the stress ratio of the column. And then you plug it in this one, you will plot the graph here. So by going back, you got this one for the design equation. Okay, this one for the test result from the lab. That's we are going to test it. And this one from the theory. You can see the difference. This graph will show you what we using is going to be based on safety. Okay, that means the graph going to be get the lowest one compared to the test result, compared to theory. In order the structure we are considered to be in safety. Okay, based on this, you can test. You can do a lot of testing. You will have the steel plate. We will use this steel plate in the form of steel column. We will plug this specimen into the 20 kilonewton UTF. Okay, and then after adjusting everything into the vertical direction, you just move the lead needle close to the back distal, and then you apply the loading, increasing the loading slowly until the column get buckling. And then when they get buckling, the lead needle will stay there. So the back needle will come down. And then this one you will get P critical. You can determine sigma critical by divided by the area. And you can decide sigma critical divided P critical by the area. And then you know the length of this. Okay, you have this one for the L. You have this one for the A. Okay, the area of this. So you can compute the radius of gyration. Okay, from the I and A. Radius of square root I over A. And then you also compute the stress ratio by plotting the sigma critical at vertical axis and this stress ratio as the horizontal axis. You go back to the previous slide that we talking about the curve from the theory that's going to be on the top of this one. And then we got the testing result that is going to be in the middle part. And then we have the design equation that is going to be the lowest one. And based on this, you should get the buckling of the steel column to show up. And you also need to calculate this one for the critical stress. Okay, and then you just plot the graph and do the discussion about the relationship between the stress and the stress ratio from three things. One is from the theoretical Euler stress equation, and one that you obtain from the test, and the one from the ISC steel design column, and you make the discussion and make the conclusion. That's all for the brief of the lab. Okay, and P. Chu Thong, our TA, will show you about the step, the testing procedure to you, and he also provide you this data sheet, okay, and make you the calculate, and you make the calculation here and plot the graph and make the data analysis, discussion and conclusion. Okay, that's all for me to lecture to you guys today.